All right, so yeah, there we go. All right, so I just have a bit of stuff today to finish up about let's see, about the hash table stuff. Specifically, we want to go over the other. I just want to mention the other strategies to use to handle collisions, and then I actually have to show that this actually is a constant time operation, because I've just been saying so, and you've been kind of trusting me that basically the collisions won't be too much, right? So what we've been doing is something called open addressing so far, right? The grand strategy is called open addressing, and we implemented it, or I implemented, maybe you went follow along too. We implemented a particular a variation of open addressing called linear probing, which just simply said we go ahead and if you have a collision, you just simply look for the next available space and take it. And next available space is defined as literally the next one down that you can find, right? The other way to do that is to redefine what next available space means. Because if you do the next available space, if you use linear probing, you're going to get clusters, right? You're going to get a bunch of items bunched together. If you use something like quadratic probing instead, that will spread it out more at the cost of maybe it takes a bit more time to resolve collisions. So rather than looking like, okay, I'm going to look 1 from the starting position, then 2 from the starting position, then 3 from the starting position, which is one way of looking at it. The way we implemented it was rather than looking to find my space, I'm going to look 1, then the next one, then the next one, the next one. But the way you can look at that is, okay, I'm going to look 1 away from my starting position, 2 away from my starting position, 3 away from my starting position until I find an open spot. Quadratic probing goes, I'm going to look 1 squared away from my position, so I'm going to look at the next spot. Then I'm going to look 2 squared, which is 4 spaces away, then 9 squared, then 16, and so on. And that's really it. There's nothing to it. Just works exactly the same way. If there's something else, I just move on to the next one. Disadvantage, things will be less clustered. Disadvantage, it takes a lot of you have to do multiplication, addition, and modulo as opposed to just addition and modulo. If it's very, very full, it can sometimes you might not find that empty space as quickly as you would with linear probing. But the other but that was still a variation of the same strategy, which was open addressing. The other grand strategy that we use to resolve collisions is kind of to just accept that they happen and use something called chaining. It's also sometimes called bucket hashing, because what we do is that we basically, rather than having an array of entries, instead we have an array of linked lists. Okay, so this is an array of linked lists, and rather than basically one space holding just one entry, one key value pair, we have a bunch of spaces. We have each space holds a bucket of key value pairs, essentially a linked list. Okay, and it works this one is actually really intuitive. It works exactly the way you think. If something gets hashed to that location, if something gets hashed to that location, you just simply add it to the end of the linked list. So basically, say Apple gets a hash to index 3, right? Well, index 3 is already occupied. What are you going to do? Well, we just add it to the end of the linked list. What if banana gets hashed to index 0? Well, we create a new linked list and add it to the end of index 0. Right? So now index 0 would hold one linked list, and a linked list with a single item of the value banana. Yes.
Is that still constant time?
It will be, believe it or not. Okay, because we have to make some assumptions, unfortunately. But we can assume that on average these will take constant time, even though that doesn't make sense. If we're unlucky, it's going to be linear time. Okay. Because what's your concern?
Like you have to go through the array and find the
right. Right, and that's going to be really bad if everything hashes to like index 0. If all the items end up in index 0, you only have one linked list, and now you're just dealing with a linked list in a very roundabout way, right? So what we need to do is we've got to rely on the fact that we basically need to assume that our hashing function is going to distribute our hashes evenly between all the indices we have. And then once the expected average length, not the average length, we're not going to bother counting, but once the expected average length exceeds a certain amount, in other words, maybe there's maybe since this is an index, since this has 5 items in it, maybe if there's 15, so an average of 3 items. At that point, we'll rehash as well. We'll go ahead and take all the items and iterate through them and redistribute them in a new linked list, right? So basically, we'll also resize to make sure it doesn't get too big, right? So we'll do that as well. Now that doesn't seem like it, but if we assume that everything's evenly distributed, right? Well, in here, and if we add 15 items, then the average amount of time to find something will be 3. We'll be fine, you know. Actually, it would be like 1. Yeah, it would be around 3, like 2.5. Okay, so the advantage of this is that basically you don't have to deal with the weird wonky, at the bottom it says, and this is I think is the big one, you don't have to deal with those weird wonky deleted nodes, right? You just simply add it. If you need to delete it, you delete from the linked list, right? If you iterate through a linked list and you don't find it, it was never in the hash table to begin with. Sorry, it's just not in the hash table. And we don't need to know it was never there to begin with. Or not. We can just simply add it to the end of the linked list if we determine it's not there. You can store more things than you have slots, which is nice. But it's very intuitive, right? There's no tricks here. Okay, but to get to your question of how do we know this is how well this performs? The way we make sure that this isn't a constant time is that we aren't measuring. We make sure that the way that we're measuring this, or the way that hash tables perform, has nothing to do with the size of the table, and everything to do with how well it's filled up, right? Like look at what its load capacity is. Load factor is. Okay. In other words, this is the parked car in a garage analogy. Basically, doesn't matter really what size of the garage is. If it's like super big or just big, right? It doesn't matter. If it's filled up most of the way, it's going to take a long time to find a spot. It doesn't matter really how big the parking garage is. Maybe if it's a little small, it'll take no time whatsoever. But once it gets to a certain size, right, finding a spot in a parking garage that's nearly full, it just takes forever, no matter how big it is. Okay. On the other hand, if your parking garage is only half full, it's big or really big or super big or something like that, right? Then again, the size of the parking lot really doesn't matter, and how many cars that are currently in it doesn't matter. All you know is that half the spaces are empty, so it's really easy to find a space, right? So the load factor is what matters, because intuitively it makes sense that basically if there's no collisions, it's just a constant time insertion, right? If there's no collisions, you just simply add or remove the item. And the smaller the load factor is, right, there's less items to collide with, right? Less the chance of having a collision. So lower load factor means less collisions, which means better performance, right? It's just kind of one of those things that logically makes sense. So the question is, how many collisions can we expect for a given load factor? It's a lot of work, but Knuth figured it out, fortunately, I think. Or the slides say Knuth figured it out, and I'm going to trust that because Knuth basically figures out everything. Knuth is kind of like really, really important in computer science. He wrote something called CalCP for short, or The Art of Computer Programming. So, or he's still writing it, rather. He's got the first 3 sections of it done. And he's been writing it for God knows how many years. One of the things he worked out was a formula for the expected number of comparisons that you have to do in a hash table that uses open addressing with linear probing. So with the one we implemented, not with chaining. Chaining uses a different equation. Okay, so let's say that our hash table is 75% of the way full, like we've done in our examples. Sorry, in our example hash table. So let's say it's got filled up to the maximum, which is 75%. After 75%, we resize. So our hash table is that was 1/2. Let's see. So 1/2. Does it show up at all? Yeah. 1/2. 1 plus 1 over 1 minus L, where L is the load factor. A lot of ones there. Okay. So let's say our load factor was 75%. So let's put 0.75 in here. In other words, it's 75% of the way filled up. So it's actually not bad math. It's not really that hard to do. 1 minus 0.75, that gives us 0.25, or 1 over 4, right, 1/4. And then you've got 1 over 1/4. So you use that rule that always seems weird, that basically you just flip it over and it's now, 4, right? So now we do 1 plus 4, which is 5, divided by 2, so 2.5. So if the hash table is 75% of the way full, you can expect 2.5 comparisons on average, right? What about like 0% of the way full? What if it's not full at all? How many comparisons is that going to take? Okay, just for a baseline, right? 1 over 1 minus, let's see, it was L. So what if L is 0? Well, it's 1 over 1 now, plus 1, that's 2, divided by 2, which is 1. So it takes 1 comparison on average if your hash table is empty, right? And that makes sense because you've got to compare that space, right? You got to check, is the space filled, right? Right, that's what you're looking at. Is the space filled or not? And here we're saying, yeah, it's filled. So, so at 7.5, with 75% of the way filled, it was 2.5, which is a pretty good number, in my opinion. It says that basically it's, let's see, oops, sorry. So 2.5, so basically you have to basically check 2.5 spaces on average, so somewhere between 2 and 3. And if we're pessimistic, it'll take 3 checks to find something. Using chaining, if the item is in the table, then on average you have to look at the table L. So basically you find the linked list, right? And then if you're trying to find an item, you got to look through half the items in the linked list, right? So assume that the lists are evenly distributed, right? So L here is not the load factor, it's the average number of items in the list. So it's the number of items divided by the table size. Oh wait, that is totally the load factor. It just can go over 100 this point. So it can go over 1 this point in this example. Why? Because you can have, like in our previous example, you can have 15 items in a table that has 5 slots because each of those slots is a linked list, right? So the acceptable load factor or the acceptable average size of a list might be something more along the lines of 3 in something with chaining. So with chaining, you have to rehash less. But anyway, the number of comparisons, 1 to find a list, and then you iterate through half the items in the list. So a quick table for those values. So if we let a table if we rehash basically when the table gets half of the way filled up, then we're never going to do worse than 1.5 comparisons on average. So that's the expected number of comparisons. Okay, this is the average case, and we have to live and die by the average case here. Okay, because worst case scenario, if our hash function has gone terribly wrong, then we have to admit to ourselves that actually hash tables are O of n, right? Worst case, hash tables are always O of n because the hash function can go terribly wrong. But on average, O of 1, right? Constant time. And why constant time? Well, because we're using this number. We're using a number like 1.5 comparisons or 2.5. And this has nothing to do with the size of the hash table. Nothing to do with the number of items in the hash table. It has to do with the percentage that's filled up. And that's kind of, that's tied to the size, but it's not, like, size itself isn't the factor that we base our final runtime off of. It's the percentage that's filled up. So if it's 90% of the way full, it will do 5.5 checks. And this is really good, actually. Like, if you're trying to search through a sorted list, right, for an item that's 128 items, you use binary search on that sorted list, it's going to take 7 checks. So a hash table that has a load factor of 90 will do less comparisons on average than a sorted list, a small sorted list. So that's pretty good. But of course, that's the average case. Worst case scenario, you could be looking at something worse. But typically in Java with their hash set, it uses a load factor of 0.75, if I recall correctly. I know the hash table data structure does, but I don't know about the hash map and the hash set. And we're just learning about hash set and hash map. Hash table is like something else, but it works exactly the same, except when it doesn't. But for your purposes, it has to deal with like concurrency and stuff, which is not really important to our discussion. But they find that this is the good time-space trade-off. that's the big caveat here also. We are shoveling space into basically a sacrificial altar as quickly as we can, so that we can get as much time, as much of a time speed up as we can. Okay, time. It's like, for instance, if I've got 750,000 items stored in a hash table, right? Then I'm probably looking at 250,000 wasted slots, right? Or if we change that to that unit of measurement to megabytes, if I've got 750 megabytes stored in a hash table, then I'm looking at maybe 250 megabytes of wasted space right there, just so that I can get that time. So time is a huge factor in these. And that's what it comes down to hash, and that's pretty much it. We already did this last part of it, which was how in the world do we implement these things. I like to do the implementation before I talk about the runtime here. So, but that's it for hash tables. Now, from what I understand, this next couple of weeks are looking particularly brutal for you in the other classes, right? Seeing some nods here. So it will be nice if we get on to possibly an easier subject, right? And the good news is this isn't a fake out. We only have 2 chapters that we have left to cover in the month we have left. Okay. The first chapter is sorting, and then we get into graphs. And graphs you probably have learned a bit at some point in math concepts, right? Right? Some of you. Okay. And I'm going to assume that you haven't anyway, but for the most part, I'm going to assume that you have learned. You probably know a bit about them, and it's not going to be too bad. But sorting, you're going to learn a lot of sorting algorithms. But with sorting, I can tell you it's going to be on the final exam. Specifically, we almost always have we've always had problems on how do you do quick sort, how do you do merge sort, but no coding. All these are conceptual questions. How do you use quick sort and merge sort and insertion sort? Those kind of conceptual questions. But we're going to teach you about a bunch of sorting algorithms. Today I'm just going to try to get 3 done. Selection sort, bubble sort, and insertion sort. Which you might all class, if you know anything about sorting algorithms, you might throw these all on the pile of terrible sorting algorithms. Which is a lie, only 2 of them are terrible. Insertion sort is actually amazing. It is my favorite sorting algorithm, because it can do something that all these fangled and fancy, log n sorting algorithms can't do. And that's do online sorting, which I'll define in a bit. So we're also going to learn our final bit of our final family of big O notation. So we've learned about constant time, linear time, quadratic time. Then we've done logarithmic, and when we cover quick sort, merge sort, and heap sort, we're going to do log linear time. With heap sort, it's pretty easy to see. What we do is we throw everything into a heap, and then we basically, remove items from the heap. If you have n items in the heap, and an item takes log n time to remove an item or add an item to a heap, well, you're doing log n operations n times, so it's going to take n log n time, right? Same with tree sort, which is not listed on here. Tree sort's actually pretty easy. Throw everything into a binary tree. Read the binary tree in order. If it was a balanced binary tree and you had n items, well, it took n log n time to add it and n log n time to read your binary tree. Congratulations, you just have an n log n algorithm there for sorting right there. Mind you, unless you're clever about it, you've got to create a tree data structure to do that, which of course takes extra space. But hey, at least now you know at least one n log n algorithm. I'm going to kind of gloss over shell sort because we don't cover it too much in the exam, but know that the runtime of shell sort is actually an open problem in computer science. We don't actually know how well it runs. We know it runs pretty well. We don't know what its bottom limit is, though. We don't know how well we can get it to run. That has been an open, and it's not because it creates shells or anything. It's named after a guy called Shell. What is sorting? That should be pretty obvious at this point. Sorting is the process of just ordering things. So the things have to be comparable, right? You have to be able to put them in some order. And it's just arranging things, and we're assuming we're arranging things from smallest to largest. Okay? If you want things largest to smallest, read it in reverse. Okay? So And what's nice about these sorting algorithms is that these are all algorithms that all do the same end result, which is gives you a sorted, a sorted list or a sorted array, right? All these algorithms do the exact same thing. They just happen to do it in wildly different and interesting ways. So this is a great way to just compare how things operate. And also we'll be able to learn about a recursive technique called divide and conquer, right? You haven't learned about, you never, even though merge sort and quick sort are much cheaper, much quicker than these other sorting algorithms, we don't bother teaching them in an earlier class, like you might have learned bubble sort or selection sort and insertion sort depending on your professor. These things don't require recursion. Merge sort and quick sort require recursion. Heap sort requires you to know what a heap is, right? And shell sort, as I just mentioned, we have no idea how that works. So, and no professor really likes to say, well, I don't know what the answer is to that one. So, okay. So, just know that that whatever you write, Java probably writes it better. And the slides here probably are actually out of they're no longer correct. Actually, these slides are outdated and incorrect, but they might not have known that when they wrote it. So Java API provides the arrays class. So you have the arrays toString class. Well, there's also an arrays.sort, and there's a collections.sort and there's a collections sorting algorithm for lists as well, right? So they're built in already. It says that it will use quick sort for the primitive types and merge sort for arrays of objects arrays of objects on lists, and that's not correct anymore. This one will not use merge sort. If you're using it on an array of objects or on lists, you're going to be doing tim sort, which was implemented in Python in 2002, and then in a bunch of other. I think it was originally created in 1993. And the only reason we don't cover it here is because it requires you to know about both insertion sort and merge sort in order to see how that works. So, and these will be generic methods, but essentially you can assume that when I'm talking about sorting algorithms, it looks like this: public static void sort a list of items or an array of items of type T, and those T's are comparable. Okay, so without further ado, let's start off with the worst of the usable sorting algorithms, right? There's other sorting algorithms like Bogo sort and Bozo sort and Stooge sort. Actually, I think Bogo and Bozo are the same thing, but Stooge sort is not with a runtime of. Actually, I shouldn't say it because guess what? It exists for the same reason Bogo sort does, which is to throw it at students for analysis. Typically, that one's used in the class, but those sorting algorithms are kind of not useful. Okay. Selection sort, on the other hand, it runs in its worst case runtime, best case runtime, and an average case runtime are all quadratic. I guess it's terrible, except it's quadratic only in one measurement. It's actually linear in another measurement, and we'll get into that. So selection sort, though, we start with it because it's really easy to understand. Okay. Suppose you have a pile of paper. Suppose you're a TA and and the papers have been graded and now you need to sort them in alphabetical order so you can return them for some reason. Okay. So what you do is you find so if you're using selection sort, here's what you do: you go through the list of names and you go for the one that's first alphabetically and put it face down, right? Then you go through the list. Then you return to your unsorted list. Go through the list of alphabetically and find the one that's first alphabetically. And put that one down. So you keep selecting the one that appears first in your unsorted pile, right? And then adding it to the end of the sorted pile. Now the difference here is that we're not going to create two arrays for our sorting algorithms. For every single sorting algorithm except for merge sort, we're going to try to do this in place, which means that we aren't going to use any extra space except for what we need to swap. Typically, this means dividing the array into two portions, a sorted and an unsorted portion. Okay. But selection sort simply says, let's go ahead and put the smallest item in index 0, the next smallest item in index 1, the next smallest in index 2, and so on and so forth until it's all sorted. Once there's one item left, that's the biggest. So we just, keep that where it is. So it's easiest to see if I draw it on the board, and I'm just going to create, and I do these of size 8. So what I typically do to generate this is 1, 2, 3, 4, 5, 6, 7, 8, right? Just list them and then put them in different spaces. So, okay. So the first thing we need to know is what is the right number to put in the first location in the list, right? So we go through and we want to find the smallest number. So 7 is currently the smallest, 2 is the smallest, 2 is the smallest, 1 is the smallest, 1 is the smallest. So we go through, we make 8 comparisons, right? We do 8 comparisons, okay? So we did 8 comparisons, and we found one was the smallest. So we swap 1 into that location. Right? We found the smallest, so we just swap it into that location. Okay? Next we need to, so 1's already in place, so we don't need to recheck it. So now we want to find the next smallest after this location. So we look at 2 is the smallest, and then we check against all the other items and find out 2 is the smallest. So we check 1, 2, 3, 4, 5, 6, 7 times. Then we do this. What do we do now that we found that 2 is the smallest? We swap it into this location. Okay, we swap 2 with itself, in other words. Kind of useless, but it's just the way the algorithm works. 3, we do the same thing. We do 6 checks. 1, 2, 3, 4, 5, 6. Right, and then swap it in there. Then over here, 1, 2. So here we do 5 checks. We find out 4 is the smallest. 5 checks to find out 4 was the smallest. Then we swap 4 with 7. Then we find out 5 is the smallest. Then we find out 7 is the smallest. We find out 6 is the smallest. Then we find out 7 is the smallest. And then the last one we get for 3, so we don't really need to check it. So 3 and then 2. So we had 8 checks and 7, then 6, then 5, then 4, then 3, then 2, and then we got the last one for 3. So except for getting the last one for 3, how many comparisons did it take? Right? How many times did we have to check, do a less than or greater than operation, right? Because that's what you have to do when you sort things. How many times did I have to do a compare to operation? Well, I did 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2. So that looks like our old, aside from the 1, that's 1 plus 2 plus 3 plus 4, all the way up to n, right? Which is n times n plus 1 over 2, right? Which is equal to n squared. Big O of n squared, right? Everybody remember this from beginning of the semester, right? Right, this is just, except for the plus 1 over there, so, and that free check at the end doesn't really impact us at all, okay? So selection sort's nice in the fact that it does do one thing that's nice, which is there's 2 ways to measure how fast sorting algorithms go. The first way is to check how many comparisons you have to make. And we typically do this because comparisons are traditionally the most expensive operation of sorting. Comparing to see if 2 items are equal or less than, because that can be complicated. But how many times the other way we can do it is look at how many exchanges there were, right? And selection sort has a linear number of exchanges. That simply means is that what's the maximum number of times items get swapped? Well, each item gets swapped precisely, we do precisely 1 swap for each iteration, right? We swap 2 items when we need to move the first item in, then swap another 2 when we need to move the second item in, swap another 2 items when there's a linear number of swaps. You do 1 swap for each item, or 2 swaps if you count. Sorry, we swap n pairs, in other words. Okay, so that's what's nice about selection sort. So let's look at the example they have in the slides quickly. So we look at we find the minimum one, and then we swap it with the location we want to put it in. We find the minimum one, which takes O of n time. Then that takes basically the number of unsorted items. It takes O of n time, where n is the number of unsorted items. O of n time, then O of n it takes n not times, then n minus 1, then n minus 2, then n minus 3, and so on and so forth. So find 35, then 60, then 65. And here it just breaks it down further, where it's just finding everything and then swapping it in. It's a very simple algorithm. So, but again, it's to n squared over 2 minus n over 2 swaps that take place. So let's see. I'm just taking a short minute. So anyway, the big thing about this is that it takes O of n squared comparisons and O of n exchanges. Now, we don't normally consider exchanges to be a cost because what I just said was comparisons are normally expensive because a comparison could be complicated. Each of the things we're sorting could be a complicated data structure that has to do a lot, that takes a lot of time to compare. On the other hand, swapping two things is very cheap. You're just swapping memory locations around, right? But suppose you're working on like a theoretical computer design where comparisons are cheap but moving things are expensive. In that case, you'd want to use the thing that takes the least number of exchanges, in which case selection sort is your guy. But most of the time, selection sort is not your guy. Now, why is this? It's because selection sort takes O of n squared exchanges no matter what. And now I'm going to brutalize some mathematical terminology. Okay, I didn't do this for the other class. I'll probably do it for them later. But I've told you that I've been using big O, and the way I've been using big O makes mathematicians like Dr. Hughes in this department very, very angry. I've been using big O to say this is the runtime efficiency, and that's not quite true. Big O is actually like the worst case runtime, or it's equivalent to the worst case runtime. It's never going to be worse than this. Your runtime for selection sort is never going to be worse than O of n squared. That's what I literally say then when I say O of n squared. And if you're rules lawyering me, your question might be, wait, never going to be worse. So you're saying it can be better, right? So we have to have, so mathematicians also have a notation to saying it's never going to be better than this time. And you'll probably learn this in more mathematical stuff, but this basically is big omega. So it's never going to be better than this, right? So you're saying it can be worse though, right? So we also have a third notation, which is typically what most computer scientists mean when they say big O, because it looks a heck of a lot like big O, which is big theta, which means it can't be any worse or better than this. Okay, but that's neither here nor there for the purposes of our course. Just know that these things exist, and most of the time when a computer scientist or a programmer says big O, they might mean big theta, and it's just a weird thing that we do. If we're being exact, we will be exact. Okay, and there's also like little o and all sorts of other stuff you're gonna learn. Okay, but we can't. But from our perspective, we're just going to talk about big O, and we're going to look at best case, average case, and worst case, right? And for selection sort, we learned that the worst. Well, actually, we learned that we didn't really learn everything. We just know it's O of n squared. We don't know where this applies. So let's look at what's traditionally the worst case scenario for any sorting algorithm, which is getting things in reverse. 8, 7, 6, 5, 4, 3, 2, 1. Right? That's typically traditionally the worst case, basically because everything's out in the wrong place. So you'll swap 1, then you'll swap 2 in, then you swap 3 in, 4 in, 5. That will take O of n squared time. Right? Worst case scenario. Right? Because really can't come up with anything worse. So what do you think the best case scenario for a sorting algorithm should be then? It's already sorted. Right? That's exactly right. It's already sorted. 1, 2, 3, 4, 5, 6, 7, 8. Well, selection sort is terrible because it's really stupid, because what's it going to do? It's going to look for the smallest thing, swap it with itself, look for the next smallest thing, swap it with itself, look for the next smallest thing, swap it with itself. It's very consistent at the very least. So if the best case and the worst case are O of n squared, well, average case is, of course, O of n squared, right? That kind of just falls in place. In fact, the only thing that's going to have a different average case and worst case is going to be quick sort. Traditionally, also what I like to use is almost sorted as well, because that gives you a much more realistic, where it's much more realistic that you get something that's almost completely sorted. Like something like 1, 2, let's say 2, 1, 3, 4, 5, ... all the way up to maybe 1 million, right? Something like that is much more realistic of the case, where you got one item swap. And again, selection sort is going to take forever to do this. It's going to figure out 1 should go here, and it's going to accidentally put 2 here. And then it's not going to put, I guess, 2 and 2 together to figure out that it's already sorted. So it's going to just, do it like a million times. So believe it or not, bubble sort is a huge improvement on this. So bubble sort is actually very simple. It works off of just swapping pairs of items. It's also quadratic in the worst case because, again, if you throw it in the worst case scenario, it's still going to, a reversed list, it's still going to take a while to do. But it's very simple, and why it often gets taught as the first sorting algorithm, which is we compare adjacent elements in the array and swap them if that pair of item is out of order. As a result, I don't know why they have that on there, but as a result, the smallest items, those go to the bottom, while the biggest items will go to the top. Okay, well, pretty much the biggest items go to the top. So let's see this in action. And can everybody see the orange? No? Okay, so 1, 2, 3, 4, 5, 6. Let's put the 8 here and the 7 after the 1. Okay? So what we do is we go pairwise through this list. So we go, okay, is 2 and 5 sorted relative to each other? Right? 2 and 5 are in order, so we don't do anything. We move on to the next pair. What about 1 and 5? Are those in order relative to each other? No. So we don't. So what we do is nothing fancy. We just swap them and fix that. So now 1 and 5 are in order. 5 and 7 are in order. 7 and 4, however, are not. So 4 and 7, then 3 and 7 are not in order. And 7 and 8 are in order, and 8 and 6 are not, so we swap 8 and 6. So what happened there? Well, 7 slowly rose basically to close to the top of the array until it found something bigger, and then the bigger thing continued to bubble up to the top. So this is why it's called bubble sort, because you're always going to end up with the biggest item ending up at the top. Right? Obviously, it's not done yet. What did doing a single run of this process do? It brought the largest item to the top of the list, guaranteed. Why? Because you're going to continuously ask items. Ask pairs, and if the bigger pair is not, the biggest item is not in the biggest location, it's going to swap with things until it is. Okay, so now we know that this subsection of the array needs to be sorted, so we can just continue. So we can basically just go through these indices and leave that one out. So we can look at one less pair, right? If we were looking at n-1 pairs, we can now look at n-2 pairs now. Okay, so 2 and 1 are out of order, so we swap them. 1 and 2. What about 2 and 5? Those are in order. 4 and 5 are out of order. 3 and 5 are out of, 5 and 3 are out of order. 5 and 7 are in order. 6 and 7 are out of order. 6 and 7 are out of order. Look at that. That just fixed itself really nicely. Okay. But logically, all we can ever know is that now 7 is in the right place. The second to last item, the second biggest most item is now the biggest. So now we just look at these pairs. So 1 and 2, 2 and 4, 3 and 4, 4 and 5, 5 and 6. So now, again, according to our algorithm so far, all we know is that those 3. Now, one of the advantages of the bubble sort, though, is now you're realizing, well, all we're going to do is we're going to look through all these pairs and not swap anything. And then we're going to look through these pairs again and not swap anything. And we're going to just keep doing that unless we have some kind of a break condition. Well, we can put in a break condition to kind of optimize this, which is what makes bubble sort just so much better than selection sort. We can have a break condition, which is that if we go through and examine a bunch of pairs and we don't swap once, we don't do a swap during a single iteration, then we know that we're done. If we go through and nothing was out of order, then everything's in order. So we can stop. So worst case scenario for bubble sort, again, is the reversed array. 8, 7, 6, 5, 4, 3, 2, 1, right? 8 has to bubble to the top, then 7 has to bubble to the top, then 6 has to bubble to the top, and that will take 7 swaps, then 6, then 5, then 4, then 3, then 2, then 1, right? So that's quadratic time. So worst case scenario for bubble sort is quadratic time. But what about our best case, where basically we hand it something sorted? Well, if we hand it something sorted, we check 1, 2, we check 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 7, 8. Sorry, 5, 6, 6, 7, 7, 8. Right? Nothing is out of order. We didn't swap anything, so we are done. Right? So worst case scenario, O of n squared. Best case scenario, O of n. That's nice. Best case scenario, linear time. And if something is partially out of order, right? If something's partially out of order, one swap to fix, go through, and then we go through again. There were no swaps, so we only do 2 runs through the algorithm this time, as opposed to with selection sort where we'd have to perform the entire algorithm. So again, that's like linear time right there as well. So bubble sort's pretty nice with that regard. So everybody got an understanding of how bubble sort works, and just that it's, that's kind of superior. Now,